of all of you. That is a heads up that, as you know, the material we're hearing today is benefiting your class this semester. And most of the most important information, in fact, 99% of the most important information is presented during the question and answer, when you find out what the other people in the audience want to challenge Professor Hoffman about. So I strongly encourage you to stick around to hear what those ideal pieces of information are. You will find them very beneficial.
Good afternoon and welcome. Can everybody hear me? Thank you. Good afternoon and welcome. It's a great pleasure this afternoon to present Professor Roald Hoffman of Cornell University. Professor Hoffman is the Frank H.T. Rhodes Professor of Humane Letters and Professor of Chemistry at Cornell, where he has been since 1965. In the person of Roald Hoffman, we have one who, for the early part of his career, has been veritably stalked by the Nobel Prize. Professor Hoffman earned his PhD at Harvard University with the Colonel, Professor Bill Lipscomb, and also with Martin Guterman. Lipscomb won the Nobel Prize in 1976 for electronic structure calculation, electronic structure work on polyhedral borane compounds. He then became a junior fellow in the Society of Fellows at Harvard with R.B. Woodward, and Woodward won the Nobel Prize in 1965 for his contributions to synthetic organic chemistry. And finally, in 1981, the prize overtook Professor Hoffman when he won it for work that he did at Harvard in the symmetry properties of paracyclic reactions. He shared the Nobel Prize in 1981 with Professor Kenichi Fukui, and had Woodward lived, he surely would have shared in the prize as well. Professor Hoffman has had a long and distinguished career. It would not do to recite as many awards, but I do want to note that he has received the Arthur C. Cope Award in Organic Chemistry from the American Chemical Society, the ACS Award in Inorganic Chemistry, and also the Pimentel Award in Chemical Education. Professor Hoffman is the only person to have received awards from these three divisions of the American Chemical Society. He is the author or co-author of 450 scientific articles and 2 books, and he describes his own research as applied theoretical chemistry. Today he will tell us in magnificent detail all the ways to have a bond, but before he does that, we have some departmental business to attend to.
Thank you, Thomas. Today it's my pleasure to pass along this distinguished plaque to our distinguished lecturer today, Professor Roald Hoffman. Normally this is an honor given to our department chair, but he could not be here today, so I'm going to deliver the plaque to Professor Hoffman. And we have this long-standing tradition of Frontiers lecturers from around the country and world to come here and speak here. And this is the 67th year we've had these Frontiers in Chemistry lectures. So it's my pleasure to give you this in honor of your visit today. Welcome and congratulations.
Thank you.
You even got my name spelled correctly. Okay, so let's see. I have to put it on the screen by pressing blank screen out. Okay, got it. Thank you. There's nothing more basic to what we do than the idea of a chemical bond. And here are 2 quotations which set the thing in perspective. Both come from theoretical chemists of a previous age, and both are heroic figures. Charles Coulson, in an after-dinner talk, says, "Will you reflect for a moment on some of the things that I've been saying? I described a bond, a normal, simple chemical bond, and I gave many details of its character. Sometimes it seems to me that a bond between 2 atoms has become so real, so tangible, so friendly, that I can almost see it, and then I awake with a little shock, for a chemical bond is not a real thing, does not exist. No one has ever seen it, no one ever can. It is a figment of our own imagination." Interesting. It's also interesting that Coulson could not put this in a paper that was published. It was only because someone recorded the after-dinner proceedings. Beautiful things like this don't find a place in papers. Just tells you something about science. And then Robert Mulligan in a typical statement, very characteristic of the way he was for anyone who knew him, and that it's not so simple as some people seem to think. So everything has a history. And let me trace, this is not the time to give a history of the chemical bond, but some of the stages. There is the idea of an element which goes back to before Lavoisier of Robert Boyle, but then Lavoisier played an important part. Dalton's idea of the atom, the idea of a molecule in the work of Laurent. The word molecule goes back to Descartes, much long before that. Then Archibald Cowper, lines in the chemical formulas and graphic formulas of Brown, and Butlerov's structures, Kekulé's important benzene ring story of structural formulas, then the idea of the tetrahedrality of the carbon atom, done independently in a remarkable achievement in 1874. Then 1916, Gian Lewis, the idea of a bond as a shared electron pair, about which I'll say something more in a moment. And the same kind of ideas by Walter Koss, although not as widely explored. And then around that time, one of the measures, experimental measures, which is a bond distance, these become to be known or begin to be known through crystallography, though until the World War II, the only crystal structures done with are the simple ones like diamond, graphite, and sodium chloride. And then the idea of quantum mechanics early on of H2, the bonding, and then the great theories of Linus Pauling and Robert Mulligan. If you want to read some more, there are a couple of references. Let me trace it in another way. These formulas are not exactly as they were written, but in the 19th century, the chemistry being mostly experimental, the chemists began to write what they called type formulas. And they were written different ways. The names of the elements were suggested mostly from work of Berzelius around 1830. So the symbols of the elements are written that way. Sometimes what we now call stoichiometric coefficients were written as superscripts. And they didn't get, here I've rewritten them in modern form. But the basic idea was you did a reaction on phenol in the middle, and you could make out of it phenylbromide or toluene as you see it left. So there was an idea of replacements, and these type formulas, without any knowledge of the geometry of molecules or anything about bonding, were just a way to summarize chemical experience. What was replaced by what? With time, it came to things like this. So here's a formula for phenol a little bit later. And I'm not writing out the C6H5 group, but that's for the students in the audience, that's a 6-membered ring of carbons. Now this idea, this all predated any idea about bond length or it was just a symbolization of what was connected to what. That's what that line meant. And the great advance of Lewis in Lewis structures around the time of the First World War, in the first paper, 1913, is to identify a line, the same line that was indicating just connectivity with a no metric on it, no distance, because the distance was, one had a general idea of the size of the molecule. That one did by the end of the 19th century. And Ben Franklin could have measured it had he wanted to, from spreading oil on water in an experiment even 100 years before then. But one knew it by the end of the 19th century, but not the idea of how big a bond, how long a bond was between atoms. And Lewis's great idea, one of many that he had, is to connect the line with an electron pair, and that came out of ideas about electrons which preceded his work by about, let's say, 20 years or so. And it was contemporaneous with the first quantum mechanics of Bohr, but was not really informed by them. It came out of somewhere else. but it did connect up to the modern electronic theory. And Lewis's great notion was to connect this electron pair and this formalism to conflate it with the idea of connectivity. And that sort of became, the two became the same thing. A line was an electron pair, was a bond. And now it is used to torture first-year students. So we write a Lewis structure. I'm sure this will appear in your exam. So you're asked to write a Lewis structure for the nitrogen molecule. So you calculate. Is this a good chemistry rule? No periodic table. I know. I'm just joking. No, leave it. It's just a joke. Everybody knows that nitrogen has 5 valence electrons, so it has 7 electrons altogether. And so 2 nitrogen atoms have 10 valence electrons. So we've got to assign 10 electrons. And what's wrong with the formula at left is if you count the lone pairs, the dots, unshared pairs, you've got no less than 14 electrons. And that's a very nice formula for N2 4-, but it's not a good valence formula for N2. And the one in the middle bottom has got the right number of electrons, 10 electrons between the line and the 4 unshared pairs, but it's got no octet around the nitrogen. So it's no good too. And finally, the one at right is perfectly okay. It's both an octet, and it's got the right number of electrons. The 10 electrons are accounted for maximum bonding. This is the octet rule. I don't want to get into it, nor do I want to tell you, though it's the greatest simple guide that also comes out of the Lewis structures, into the 18-electron rule. You can ask me afterwards to give you a proof of the 18-electron rule for organometallics and inorganics, many of them. And we've extended those ideas with ideas of electron-rich and electron-poor bonding, and that way can account qualitatively using not much more than Lewis formalism. The last 2 things do come from molecular orbitals. We can account for the bonding in most molecules in this world for the covalent side of the bonding, and then we have something else, another way of talking about the ionic one. But I really don't want to talk about this, so I'll get back to this. These are obviously, I just want to sketch sort of the framework which we're working in. Let's talk about ways of probing bonding experimentally. And I'm going to talk about these. Distances, electron densities, a little later on, dissociation energies, energetic criteria, force constant criteria, vibrational frequencies, and then magnetic and spectroscopic criteria of one type or another for bonding, just to see the various ways if we take an overall look of chemistry. So one thing I need to get out of the way a little bit is we do have this general idea of a potential energy curve. And we know that also that in molecules, so this is a plot of the energy versus a distance. And we also know that in molecules, the vibrations are quantized. And we also know, and this is relevant to the experimental measures, we also know that each observable or experimental measure carries with it a possibly different average over the vibrational energy levels. So when you measure what is the bottom of that curve, which is a theoretical one, which may be constructed from experimental facts, that may not be the same distance as it is in the ground vibrational level, which may or may not be the same distance, depending on technical word anharmonicity, for instance, in the higher levels. And when you look at any observable, you have to worry about what kind of average that you're taking. Okay, we understand that we're not going to worry about that. Let's talk about distances. So here is an easy one. Jay Siegel, a friend, has gone into the Cambridge structure base. The Cambridge structure base is a great compendium of every crystal structure that's ever been done. Maybe 350,000 such structures. And he hasn't picked out every carbon-carbon bond. Oh, he's picked out 10,000 cc distances at random. And these CC distances are of a very special kind between, not a very special, it's the most common kind. It's an ethane type distance between what would be normally called two sp cubed carbon atoms. And so two carbons which are coordinated to 4 atoms altogether, and this is the distance between them. So you see here a pretty normal distribution around 1.54 angstroms. So you don't need a theoretician to tell you that a CC distance is 1.54 angstroms. This is the experimental, with all the caveats about how good or how bad the structures are. Let's not take any pictures. Afterwards, I'll be glad to jump up and down for everyone. And was disturbing a little throughout. Now, sometimes these distances, this is very clear that a CC bond is 1.54 from this distance criterion, but this is only a product of the last 30, 40, 50 years that we have these distances. Sometimes things are not so clear. So here, for instance, or they're more interesting. The two go together. Here is, for instance, a similar plot from the Cambridge crystallographic database for iodine-iodine distances. And what you see is not a single peak, but you see there are some short distances. This is in angstrom units, 10 to the minus 8 centimeters on the bottom. That's the number of such distances. Now, mind you, iodine itself, I2, is not in the Cambridge structure base, because the Cambridge structure base, you have to have at least 1 carbon in there. So it's not organic enough, iodine. So these are iodine-iodine distances in molecules which have some other organic shrubbery around, so as to get into the database. So it's a subset of all iodine structures, but you still see a lot. When you see 300 here, that means there are 300 distances in this histogram. This file has thousands and thousands of structures. So what are these? Well, first of all, what is a normal iodine-iodine distance? So a normal iodine-iodine distance, and what is a non-bonded iodine-iodine distance? What is a van der Waals contact for 2 iodines? Again, you don't need a theoretician for that. You just look at the structure of, for instance, solid iodine here. All of us have seen this beautiful violet compound. What you see is 2.66 with all the caveats about what average over vibrational level that represents and how good that structure is. It's pretty good at 110 K. Is structured, that's at 2.66 is an iodine-iodine single bond, and 3.50 and 4.27 are things which define roughly the van der Waals contact between 2 iodines. It's not any one number, it's a range of numbers. And so to go back to the structure left over here, all the things which are from 3.5 angstroms to the right, almost all of them are non-bonded iodine-iodine, slightly attractive van der Waals contacts. 2.66, which is right at the beginning over there, is the iodine-iodine distance. But what are those other things? Well, what is the rest of that stuff near the beginning, if it's not iodine 2? Well, what it is, a large part of it is you see it right. It's triiodide with a lot of organic counterions. Lots of structures of this, centering at about 2.95, a nice typical distance. And these have been plotted out, and this is a very interesting story. This is a classical Birgi-Dunitz type diagram, one of the great achievements of structural crystallography, done avant la lettre by Henry Bent in 1968 on a basis of 3 distances. The first Birgi-Dunitz diagram was not done by Birgi and Dunitz. But what it is a plot of all the ones where you have 3 iodines, now plotting one distance versus the other. You see a beautiful hyperbola. The bunched up points are the symmetrical ones, centered not at 2.66, which is the normal iodine 2 distance, but at 2.95, which is the distance of triiodide. And the things that are unsymmetrical is one bond getting longer, the other bond getting shorter. And that accounts for many of the structures. I'm not going to go into this, but the triiodide bonding is accounted for by something called electron-rich three-center bonding. Goes back to Rundle, Pimentel, and Lipscomb, involving 3 orbitals and 4 electrons. And the ones which are asymmetrical, where there's one iodide close to an iodine, merges into a three-center bonding through another set of concepts, which you can think of as a donor-acceptor picture, where an iodide is attacked as a donor. No one would accuse iodide of being an acceptor. Iodide as a donor approaching an iodine molecule as an acceptor through the only acceptor function the poor molecule has, which is the sigma star orbital of the iodine molecule. It still is an attractive interaction, and you can count now. So what we have accounted for is actually a lot. The triiodide is the big peak at 2.95 with a normal distribution going down to each side. That's the, this is the electron-rich three-center bonding. Over at the right are charged our van der Waals interactions. Over way at the left, at 2.66 is iodine, which there aren't many. What are the other things? For instance, what is that peak at around 2.75 that you see here? What those are polyiodides. There is In minus, where N is number 4, 5. I've seen them up to 27. And what they are essentially extended structures in which, like triiodide, linear, sometimes taking right-angle kinks, I don't have a picture of one, which are contain more or less iodide ions and I2 molecules. That's why they're shorter. Okay, so why do I show you this? The reason is I just want to show you that the idea of what is a bond is, first of all, not so simple once you look at it in detail. This is one particular example. And there's a range of things, and we had to use more or less 3 or 4 groupings to account for the general shape of this. But it's also understandable, and it also can lead to various pieces of understanding of this. The whole idea of electron-rich three-center bonding evolved not from triiodide so much as from xenon difluoride, trying to account for the bonding in the noble gas compounds. And you can make sense of this, and this database is itself the source by knowing the structures. But it's the way of talking that's interesting here. When you see a distance that is similar to a single bond distance and much shorter, but maybe longer, but much shorter than a van der Waals contact, which you don't need a theoretician to tell you, you tell from the structure itself. When you see such a distance, you begin to wonder, how could it come about? And it's in the nature of human beings. If there is something to be explained, they'll find an explanation. So that you find out something about this. Now, sometimes the story is, sometimes the distances. We're talking about distances as a criterion for bonding. Sometimes the molecules tell you the story themselves. Here is a set of compounds which come from the work of Heinrich Warenkamp almost 30 years ago. And they involve a series of 3 transition metal compounds which have the shape. You see each metal is approximately octahedral. 4 carbonyls on each metal, 2 bridging phosphido groups, and the metals vary manganese, chromium, vanadium. Now, I love that. When I see it, my heart goes up. Because why? Because it's a typical thing of varying one variable that science is about. It's the same molecule, and all that's varying is the metal, manganese, chromium, vanadium. Now, as a theoretician, I know, and you would know if there were a periodic table here, that manganese has 7 d electrons, it's group 7, and chromium is 6, and vanadium is 5. And so that the number of electrons is varying. That's the only thing that's changing. I like that because it gives me a chance to say something about it. And so Warenkamp did the structures. The structures look as the ones at lower left, but he did something more. Now, something about this, and this has to do with the 18 electron rule. So this is talking mainly to the inorganic organometallic chemists in the audience, but The PR2 here, you can do it in a number of ways, but I'm counting here the PR2 as PR2 minus. And so I'm counting the metals in oxidation state 1, but it doesn't matter how you count it, it's going to come out the same. So how many electrons if the metal is manganese? If manganese has 7 valence electrons, manganese plus 1 has 6 valence electrons to play with. And then it's surrounded by 6 lone pairs, and that times 6 times 2 for the 4 carbonyls and the 2 phosphido groups. That makes 12 electrons there, plus the 6 it has makes 18. So it doesn't need any more electrons. But if you do it with chromium, you have 1 electron less. So you come up to 17, and then it needs 1 more electron and it gets it by forming a bond with the other manganese in a simple electron, in a simple kind of manipulations of the 18 electron rule. And then the vanadium would form a double bond. So the application of the 18 electron rule and carbonyls and phosphido groups are pretty good things for where it might work. It fails in a number of instances. We understand very well where it fails, or where it's likely to fail. This is a place where it might work. And so one would expect a shorter bond between the chromium compound, between the metals, and then in the manganese, and then a still shorter bond in the vanadium. And what Varenkamp did is simply beautiful and is shown at the right over here below. He plotted out all 3 structures in the same coordinate system. And now there are carbon monoxides standing up. Carbon monoxides standing up like that, you know, they're bonded to the metal down here, but they're also feeling each other. And they have a comfortable distance to be at, which is a van der Waals contact, which is about 2.9 angstroms, which I could tell you where I get that number for. So if the metals underneath want to go closer together, the carbonyls may like it or they may not like it. Look at that. As you go to the vanadium, they just bend away. I can see no more clearer illustration of sort of geometrics of molecules at work in a bonding than something over here. So the distance actually shrinks by a full angstrom between the manganese compound and the vanadium. And I assure you that neither the ionic nor the covalent radii of manganese and vanadium differ by half an angstrom to do this. This is metal-metal bonding at work and showing up in these structures. Okay, that's the end of the distances. We could go on. There are lots of interesting things. So what I'm trying to show you is how the distance criterion is used for the presence or absence of a bond. Now, what about the energy criterion? So we do thermochemistry, and we can get bond dissociation energies. To break ethane apart into 2 methyl radicals costs almost 90 kilocalories per mole. And no surprise, to break a double bond costs a lot more, not twice as much. And triple bond doesn't cost 3 times as much, but more. It scales in that direction. Now, the criterion is not, you have to be careful. One of the interesting things, now this is hard to believe, I know, but so you have to check the original reference if you don't believe me, references, but it takes less energy to break disilylene, not a very kinetically stable molecule in general, but can be studied, into 2 silylenes or carbene-like analogs, SiH2. It takes actually less energy than to break disilane into the ethane analog into 2. So you have to, silicon. Here's a comment on this. I love silicon. But it is weird in a number of ways. This is one of the ways, and why this is so is an interesting story. That's all I'll say about bond energies. Though there's a little bit more, which I'll come back to at the end. Here is C2, a diatomic molecule which can be observed. You haven't seen any bottles of C2. This is another story which we don't have time to go into. The difference between thermodynamic stability and kinetic persistence as they go into the meaning of the word stable in everyday parlance in chemistry. Roughly, the summary is like this. When physicists say stable, they mean probably 95% thermodynamic stability and 5% kinetic persistence. When chemists say stable, they mean 95% kinetic persistence and 5% thermodynamic stability. Every organic molecule in our bodies in the presence of oxygen, that means me, is thermodynamically unstable. We burn. It's a little hard to get the fire started, but we burn. The piece of paper, I don't have a piece of paper here. Here's a piece of paper. This, in the presence of oxygen, is not stable. It burns. You demonstrate this, but it takes a match to set it off. Everything in this world almost is thermodynamically unstable. That's not quite true, but things are so that C2 is C2 is the second most stable diatomic of the first row. It is more stable than O2 and than F2 with respect to atomization. But you don't have any bottles of C2. It polymerizes. It's found in hydrocarbon flames. It's responsible for some of the color of hydrocarbon flames, but it goes on to soot. And then the soot eventually burns as carbon dioxide. So it's not very stable. But there are many excited states of C2. Here are some potential energy curves for them. What I just want to show you is this something interesting about this correlation of strong bonds with short bonds, which is one of the linchpins of our understanding of bonding. There's actually a triple correlation, known as Badger's rule, that strong bonds are short bonds and will have higher vibrational frequencies, higher force constants associated with them. There are some interesting violations, and when there are violations, they're very interesting. But you can see one of them. There is an excited state of C2 about the one that's labeled triplet sigma U plus and singlet sigma U plus, which has a bond length, which is shorter than the ground state of the C2. It surprises no one that the excited states are longer than the ground state because they're weaker, they're higher up. But you can see it in that curve. There is one of those curves which has a minimum that's closer in than the ground state. And that's very interesting. But it's just a little caveat on the bond distances. Let's talk about vibrations, in fact. This is a molecule Professor Pearson will know, and trimethylene methane iron tricarbonyl. Something nice happened. These things in vibrational studies of inorganic complexes, U.S. government granting agencies decided a few years ago not to invest in these, so there haven't been done too many of these. But here there was one done in 1 year by two different groups, two very good groups, did a complete vibrational force field analysis of trimethylene methane iron tricarbonyl. That two groups do the same thing is a tragedy for the groups at the same time. It's wonderful for the rest of the community. It's the best thing in the world that could happen, because there is no chance in the world that they will be doing the same thing exactly. And therefore you forget about the standard deviations that they put on their errors. You just look at the final thing and you see from the comparison of what they have done, how people can differ or what really the real deviation or sort of uncertainty in a measurement is. So one of these groups in a force constant analysis, in a typical analysis of the vibrational spectrum, you have the vibrations and then you assume force constants and then you try to fit the two to each other. See what vibrational frequencies are given by the assumption of force constants. These force constants are essentially little springs, and you're assuming something about the strength of each spring. Well, one of the groups just put one spring between the iron and the whole organometallic C4H6 molecule up above. And the other one put in 3 springs to the outer carbons and none to the central carbon. Okay, and then they did this, and here are from the two groups the force constants that you got from this. And you see some of them are the same. You wouldn't expect them to differ on how much energy it takes for a carbon monoxide to go like this. That's that big force constant of 16.51. They're not that different. But then there are some that are off by a factor of 2 from each other. And each of them has enough of an uncertainty that they quote it to 2 significant figures after the decimal point. But really, of course, and it's not a systematic error, it's something else here, and that's going on. Foyle-Miller, who did this, is an extremely good, honest spectroscopist, and it's worthwhile reading this, what he says. 2 different valence force fields are now available for this molecule. Both reproduce the starting frequencies well, but the individual force constants differ considerably. Is either set right? We believe that most force constants which have been derived should be regarded with skepticism. There are several sources of uncertainty. First, a few of the assignments are probably wrong. Very nice. That's true, but it's very nice to see someone say this. Second, assumptions are invariably made about some of the interaction constants. Notice he's not saying the other group's assignments are wrong. He's saying assignments can be wrong. That's real scientific honesty. Second, assumptions are invariably made about some of the interaction constants. Third, it's known that refinement procedure can converge on different sets of answers. And then he says, so this is one of the ambiguities you should be aware of about a number of experimental measurements and the kind of psychology which is behind those white guys in coats in commercials on TV that scientists are always right really has nothing to do with the work of an honest scientist, as you see represented over here. Okay, then there are briefly something about magnetic criteria. Magnetic criteria are especially important for bondings which are weak. And then the story is pretty obvious, and chemists in the audience are aware of what it is. And that is when you have 2 levels, call them here A and B, they may be of the same symmetry, of different symmetry. Here they are of different symmetry. One is representation A, another representation B. And you have 2 electrons to put in those levels. There are 6 ways of assigning the 2 electrons, 3 singlets and 1 triplet. And the real ground state of the molecule will be a competition. If the splitting between the levels is small, this is the classical diradical situation in organic chemistry. It's what happens for cyclobutadiene. It's what happens for trimethylene methane, the molecule I showed here. It's what happens in inorganic systems for high-spin, low-spin systems. If you're looking at a D8 octahedral complex or a D2 one, this happens time and time again. 2 levels, 2 electrons. If the 2 levels are not split by, the competition for being the ground state will be between 2 electrons in the lowest level mixing it into itself through configuration interaction, the 2 electrons in the higher level, that is a configuration A squared with a little bit of a B squared, and that competing, the singlet of that competing with a triplet from assigning 1 electron to each level, the high spin. If the splitting is small, the triplet has a chance and usually wins out. That's the high spin ferromagnetic situation. If the splitting is large, a triplet has no chance at all, and the ground state of the system will be a singlet. So this is the magnetic criterion for whether there is a bond or no bond, and the splitting of the levels identify large splitting with the presence of a bond. And that leads to also the spectroscopic criteria, which is usually based on red or blue shifts of a transition. And if there are 2 levels, again, that are close to each other, now we're talking about the electronic transition, 1 electron jumping from level B to level A. If the bonding is large, then this will be blue shifted. The transition will be at higher energy than if the bonding is small. So that's sort of the end of what I haven't talked about magnetic resonance and other criteria, and there are lots of still others, but I've given you a brief tour through what I think is a realistic estimate of what is out there in the literature in terms of different ways of evaluating is there a bond or not a bond experimentally. Now, let's see. This is a cultural test. What is this? Good. Is this penetrated this far north in Ohio? Yes. Oh, my God. What is happening to America? I thought it was Cincinnati just that you had to do this. So why do I show you this? That's because it has something to do with all the ways to have a bond. So now this is much too low level. So let's look at this. This is the long way from Cincinnati to the Vatican. But Raphael painted a mural. The colors are off here of philosophers in Athens, and this is a central detail of that mural. And there is Plato at left and Aristotle at right, and to be sure that you knew who was Plato and who was Aristotle, because that was a problem for kids in the 17th century, 16th century, as it is today. Each of them is carrying a book, and if you could read on the spine of the book, Plato has Timaeus and Aristotle has his Ethics here, so that you know who wrote who was who in this. Anyway, Aristotle, we think of Aristotle as a highfalutin philosopher, but he also wrote a book which described in sufficient detail the snails from which you could get a purple pigment, the Criterion purple, in sufficient detail that anyone could reconstruct the making of that purple today. He's down to earth. Sometimes the experiments aren't interpreted correctly, but it's actually, even though a lot of interesting things in science arose out of struggling with Aristotle, Aristotle was very important, and it's pointing down to earth here. And Plato is talking about the ideal up there. And so in some way, to me, Aristotle represents actually experiment, and Plato represents theory. And you can make your own judgments on what is important. So let's talk about theoretical things. So we're going to talk about ways of analyzing bonding theoretically. Orbitals and the associated measures of bonding in orbitals. Something about quantum theory of atoms and molecules, and Bader's analysis and bond critical points, something about electron localization function, and a few other measures. I won't have time to do this in much detail, but let's do something, first of all, that's probably done at a level if molecular orbital theory is done in some introductory course. This is the electronic structure of diatomic molecules. And so the picture begins. This is the molecular orbital way of looking at bonding. The picture begins with, say, for taking two nitrogen atoms or two carbon atoms, interacting with each other at 2s and 2p. The 2 s's interact most. You get a bonding, anti-bonding combination, as you see here. The 2p's interact. You get a bonding combination of the sigmas, which splits from its anti-bonding counterpart by a different amount than the bonding combination of the pi's. And then you put into this 10 electrons for the nitrogen molecule, and you could count up the number of bonding and anti-bonding orbitals filled, and you would get a total of 3 bonding orbitals filled, each with 2 electrons, and you get assigned maybe a bond order of 3. Primitive. One has to do better. The first way one has to do better is that this is really a 0th order picture. And the first correction to this is to allow what is in fact gigantic, and that is sp mixing. And so an s orbital on one atom interacts just as much with a s orbital on another atom as it interacts with a p orbital on another atom. These overlaps are entirely comparable, so you have to put that in. When you put that in, you get actually a much more realistic picture in the sense of a correspondence to the Lewis structure over here, which has 2 lone pairs and 3 bonds, a sigma bond and 2 pi bonds. Because when you put in the sp mixing, you get the orbitals that are at right. The lower orbital, which is a pure combination of 2 s's, becomes a bonding orbital with some p character mixed in. And the next combination, the antibonding combination of sigma u over here of the two s's, actually mixes in p character to hybridize outside and becomes a lone pair combination, pointing out. The pi orbitals stay untouched, but the very important 2 sigma g orbital, which is the bonding combination of the two p's pointing toward each other, mixes in s character. Now it mixes in again to hybridize out and to make 2 lone pairs pointing out. So that in the real picture, and it also gets destabilized in the process, so it goes above the pi's. The real picture is a bond, the lower level, 1 sigma g, 2 lone pairs, 1 sigma u and 2 sigma g, delocalized, but roughly the equivalent of those lone pairs, and then a pi and a pi star orbital. And to each of these orbitals, one can assign a bonding character. So one can say that the lower orbital is very bonding. The next one, 1 sigma u, is more or less non-bonding, maybe slightly anti-bonding. The pi u next, which you see at left drawn out, is bonding. And the 2 sigma g, a very important orbital, the highest filled molecular orbital, and N2 is non-bonding, maybe slightly bonding. And so the kind of question which you can ask students, and it's a real question, is if I take N2 and if I ionize it and make N2 plus, what will I do to its bond length? Not much, because I'm taking electrons out of a non-bonding orbital. But if I add an electron to it to make N2 minus, I fill the pi star orbital, and that is filling an antibonding orbital, and so that it is destabilizing. The idea of bonding, antibonding is very useful. We'll see it in a moment. Now, if you want to attach a measure to this, to go beyond the simple bond index of 1, 2, 3, you can do the molecular orbitals, and you can do a normalization. This is called a Mulligan population analysis. And a particular measure of the bonding is if you take this molecular orbital, which is a linear combination of atomic orbitals. I don't have a pointer, but I can create one. Just bear with me just a moment. If you take this molecular orbital over here, ooh, this is nice, and you integrate it squared, which is what you're doing here, and like any self-respecting orbital, it has to be normalized. Oh, I didn't want to do that. You don't want to hear it again. Okay, let's see. We'll get there. I'm not going to use that. You can get that 1 to be a sum of the coefficients squared, and then this peculiar looking term, product of 2 coefficients times an overlap, that turns out to be a Mulligan overlap population. And it measures bonding, so it would give a large number for the 1 electron in the pi orbital of N2, a large positive number. Not 1, it doesn't scale 1, 2, 3, but it scales in some way. So it's more, and if you put an electron, if you evaluate this for a pi star orbital, it will give a negative number. If you evaluate it for one of those things I've called a lone pair, it'll give a small number, positive or negative. So you can use that to, in fact, evaluate the various, I'll do this at the end, distances in the C2 molecule. Okay, I'll come back to this at the end. Let's go to the second. This is a sort of a brief capsule of each of these ways. And I wish I had much time to give you examples. Next is Bader's he's the primary proponent of what he calls quantum theory in atoms and molecules now, or atoms and molecules. Here are some references to it. And he'll be here next week to talk about this. So what is this? This is an idea based on the electron density. And it goes like this. Here is a calculation, for instance, of the electron density in a BF3 molecule. And at the top, it's in the plane of the BF3, and in the one at right, it's cutting through a BF bond. Now, if you look at the electron density, and there are some properties of the electron density, such that the gradient of the electron density, if you evaluate that, the gradient vectors all terminate at a nucleus, in the vicinity of that nucleus. And you can use, so here are some graphs. Over at the left, you see it in the plane of BF3. In the center is the B, and all the lines of the gradient terminate at the B. And near the fluorines, they all terminate at the fluorine. And then there is a ridge between which is uniquely defined between the boron and the fluorine, and between the different fluorines. And that ridge is incidentally very nicely, pretty much independent of the quality of the calculation that you use. Not exactly, completely, but not bad overall. So you have this, so the results a surface by which you can divide all space into basins where you say all the electron density, based on this gradient of the electron density, that all the electron density belongs to this atom. All belongs to boron or fluorine. Okay, the next idea that he had was the idea of a bond path. So now if you move between two atoms, this is, let's say, a boron and a fluorine, and if you actually look at the density, now not at the gradients, but at the density, and you look at the density, then the bond path he defines as the line of maximum density linking the nuclei of the two atoms. Let's see if I go to the previous one. So you can go between the two atoms, and you can define something which is a maximum along that line, but falls off to the side in 2 dimensions, and then is this is what he calls a bond critical point, the point along a bond path where the density is minimum, actually, not maximum. I have this wrong up in the first slide, is the minimum, but the maximum with respect to the 2 other directions. He called this a bond critical path. And you get some nice things from this. And some of this can be studied experimentally. This is where I get to electron densities, which I skipped from the experimental criteria. And crystallography, you can, if you do very good, especially a combination of neutron and X-ray diffraction, you can actually get experimental spin density, experimental charge densities, which you can invert into one of these maps and compare to the calculations. This is the kind of work which Phil Coppens, for instance, at SUNY Buffalo has done very nicely. And here's a typical Coppens map for, methyl carbamide up here. And you can see regions. Clearly, that's a nitrogen. There's a carbon. They don't look like balls. These are not the balls of your spherical space-filling models, but there are regions dividing up space into one or another. That looks very good, and the idea of a bond path looks very good. But now there are troubles. And one of the troubles are, 2 troubles are illustrated. Turns out that this is a topological feature of interacting densities of anything under the sun, and doesn't look like it has all that much to do in some ways with bonding. For instance, what you see at the right over there is biphenyl, 2 benzene rings joined by a single bond. And you see the little red dots, those are the bond critical points, and they are where any chemist, before they've had too much to drink, would think that they should be. That is, at the center of each carbon, not center, slightly off to the hydrogen of each CH bond of biphenyl, and also between, centered exactly almost, between they don't have to be by symmetry, between 2 CCs, but then you see a bond critical point between the 2 hydrogens. This is a planar conformation of biphenyl. Everyone knows that the 2 hydrogens in biphenyl are in steric trouble in that planar conformation. That's why the molecule rotates. There is a bond critical point. The same thing happens for the 2 hydrogens in steric trouble in phenanthrene that you see at left. The beautiful thing at the bottom is actually horrendous. This is helium inside C60. Okay? You can put helium inside C60. It's not done by sporting methods. But you can put helium-660 and detect it very beautiful work of Martin Saunders and others. And if you no chemist would think there is a bond between a helium and what you see here is 60 bond critical points between the helium in the middle and the carbons, every damn carbon of the C60. You also see in the middle of the CC bonds, bond critical points. You will get a bond critical point between two helium atoms pushed to each other at every distance. You will get a bond critical point between two ammonias in which a Maxwell demon compels to come onto each other so that the lone pairs are pointing toward each other. Nothing which two ammonias would do in their sane mind. So this is a topological property of the electron density, but it sometimes coincides with chemical experience about bonds, and sometimes it doesn't. Okay, let's talk about ELF, and I'll say something more about this. ELF, an interesting measure. If somebody comes to you and shows you, these are very popular, but especially by some inorganic solid-state chemists, shows you an ELF plot, what you should do is innocently raise your hand and ask, I'm sorry, I don't quite understand. Could you explain what ELF is? And then you watch the person squirm. So let me tell you the big secret what ELF is. So ELF is a way of trying to identify regions in a molecule where there are two electrons with paired spins, one up and one down. Somehow it's easier in terms of identifying those regions to identify regions where two electrons are not paired, where two electrons are of the same spin, pointing up. And a general philosophy underlying ELF is where there is a large density of two electrons of the same spin, there will not be a large density of two electrons of the opposite spin, and vice versa. So they try to identify the pair probability function of electrons of the same spin. Now, the reason they're going the curvature of the pair, why are they doing the curvature? The curvature is the second derivative. The reason they're doing the second derivative is because the actual probability of two electrons being the same spin being in the same place is 0, so is the first derivative, and so the second derivative is the first thing that doesn't vanish. Okay? So you're doing a Taylor expansion, and they're focusing on a second derivative. And now that's this f of r, and then they want to normalize it, so they compare it to something very unchemical, which is a free electron gas. And they say it's the curvature, second derivative, of the pair probability function of electrons of the same spin relative to free electron gas, and then they put it in a 1 over 1 plus f of r squared form in order to make it come out between 0 and 1. That's just a typical mathematical trick. There's nothing bad about this. But essentially, summarized in its essentials, is if you have a high probability of electrons of the same spin, then you have a low ELF, and when you have, that means that there isn't, if you have high probability of this, there's low probability of this. Okay, and then high ELF is where you have low probability of this, which means high probability of this. Okay, now let's see how it works in practice. Now here is some typical ELF for small molecules. People usually don't show you this. Here is one, for instance, at the top for water and for ammonia. You see those orange, nice, plasticky looking things at the top? That's the lone pairs of water. That's places where there's a high probability of two electrons of the same spin being localized. And ammonia, you see the lone pair in ammonia. Down at the bottom, you see a typical ELF picture for a molecule that all of us know. That's acetylene, ethyne here. So that little peak, little torus of green is the triple bond. There's a high cylindrically symmetrical. There's a high chance, there's a high ELF, high chance of the electrons being that way. And the light blue things are the CH bonds. Well, it's okay. It tells you where the bonds are, but it doesn't look very acetylene-like. And now let's talk about, I think that both of these measures, the critical bond path, the AIM and ELF, are inherently not very chemical. Let's talk now a little bit about theories. Why one should accept a theory, let's say that there is a chemical bond or there isn't. The usual sort of talk about theories is that we accept theories because they explain better or more of what we understand, and they make predictions of what we haven't yet measured. Ideally risky predictions. That's the usual kind of talking about theories. But I think there's much more. This is from an article I've written. I think there are aesthetic reasons. We are very simple human beings, and we fall for simplicity every time. Have you had your primary yet? No. Okay. So think about political ads. What are political ads? Political ads are the most intensive piece of visual art psychology and poetry that money can buy, which is almost as good as a Super Bowl. We're about to see the Super Bowl in 10 days. And now watch Super Bowl ads. They're fantastic. But they're political ads or Super Bowl ads, not political. There's Super Bowl ads that are okay. It's clear someone is selling you. Political ads, what's going on psychologically is they're trying to establish a link between the simplicity of our own minds and our wish for solutions to complex problems of this world and the simplicity that they project of the candidate's position. It all is something going on here, and it's wonderfully done, but it's nefarious. So scientists think they're better than this, but scientists will fall for simplicity every time that you give it to them, just like the people that the political ads fall for the political ads. This is what's behind some physicists thinking that a theory must be right because the mathematics is beautiful. This is what's behind us inevitably accepting if you have a chemical reaction and you have a mechanism that goes in one fell swoop. I've made a good living off these. And if you have another mechanism that goes in 37 steps, people will fall for the one with one fell swoop. And this is what's behind people liking dodecahedrine better than they like hemoglobin. One is simple and symmetrical. The other one looks like a holy mess, like a piece of spaghetti coming out of some primeval pasta soup. So aesthetic reasons are one reason we accept theories. Another reason is storytelling. Good stories go a long way. And I'm as guilty of that as anyone else. Frameworks of understanding, that you form a good thing which ties things together. Social needs of the community is something that scientists really think that they have nothing to do with. If you want to read a good thing about the story in biology, Evelyn Fox Keller's Making Sense of Life is a wonderful book. She says a description or phenomena counts as an explanation if and only if it meets the needs of an individual or a community. And she means social and cultural needs, even in science, and she shows it for biology. There are other things which make people accept theories. One of them is that theories that are easiest accepted are theories that are portable. That means you don't have to go back to the originator of the theory in order to get an answer. Now, that may be a commercially valuable discovery, but in the world that I move in, if you can give away a theory, that's you gain much more. That's why it's very painful, because before you've gotten to exploit it, other people jump in and do it, but theoreticians should be very happy about this. The other thing is theory should be productive, and I mean productive of reality, which means experiment. So the theories, this is what's behind also some theories which are absolutely false, being actually useful. You know, Priestley and Scheele were not dummies. They believed in phlogiston. And for 100 years, people believed in phlogiston, a wrong theory. It was productive. It not only produced explanations, it suggested experiments. And there's something to be learned. But in general, theories that suggest experiments are going to be believed. And so my personal opinion is that AAM and ELF are analytical and descriptive, beautiful in that way. But they are neither predictive nor productive. I have not seen a single chemical experiment that comes out of AAM analysis. Now, next week you will hear a rather different story, and I'm glad I went first because he will tell you, Richard Bader will tell you that this is all false. And so that is instructive. I was going to talk about natural bond orbital analysis. This is a much more chemical way of looking at this, comes from the group of Frank Weinhold. It has a large theoretical framework in front of it, a framework which is almost beyond belief, involves a number of matrix diagonalizations and orthogonalizations. But at the end of it is something which looks very chemical. And for instance, when they do a natural bond orbital analysis on methylamine, which you see here, they get a hybrid on carbon and a hybrid on nitrogen, just like the hybrid you imagine. And they get a CN bond and an anti-bond orbital, which looks just like what we want it to look. And but again, ask somebody what they really did to get this. And it's interesting. There's a lot. I don't have time to tell you. Then there's an energy decomposition analysis, which comes out of an attempt by Keiji Morikuma to divide up the total energy of a molecule, or from pieces of a molecule as it's forming, to divide that up into components correctly, quantum mechanically, not in the rough way that I did it in that C2. It was expanded by Rauch and Ziegler and is implemented in the ADF software package. And you get the division of the energy into you prepare the fragments for bonding, and then the fragments interact. And the interaction energy has a piece which is electrostatic, which just comes from, is not just repulsion, it's the electrostatic interaction between the unperturbed charge distributions. The way that this talking here is very close to what Al Anderson has studied over the years about electron density. And then there's another piece which is what they call the Pauli repulsion, which comes from introducing antisymmetry into this. And then there is the orbital interaction, which is the only piece that you saw analyzed roughly in that C2 example. And here is a typical thing for ethylene, acetylene, a large interaction energy of 114 kilocalories for ethane, 280 for acetylene. This is from pieces of methyl or CH, is broken down into a Pauli repulsion that's a large positive number, an electrostatic interaction that's negative, or orbital interaction that's negative, to get approximately at the end a dissociation energy that's not too bad for this. But it's a way of analyzing that. The problem with this is that the pieces are uniquely defined but totally arbitrary, what they do. So that they're uniquely defined. So somebody else doing this analysis will get the same numbers, but you don't know, they're not totally arbitrary, but there's a lot of arbitrariness in this. And it leads you, for instance, to a belief. Here's a typical thing from a paper by Franking, who is one of the proponents of this. So he's analyzing the bonding in diatomic molecules. And he's coming to a conclusion, what is the bond type? And he says, well, C2 is bonded by a pi bond, and N2 is dominated by electrostatics, and O2 is dominated by electrostatics, but F2 is dominated by a sigma bond plus electrostatics. Is this going to sell to someone who is used to single, double, and triple bonds? I don't think it's going to sell. It doesn't, it's not also not productive. It doesn't tell us, okay, now this is the story. So if experimentalists cannot agree, would you expect theoreticians to agree? Much less so. Theoreticians are not dealing in reality. Up there, Plato's pointing. There is nothing real there. So you will get much more disagreements. I want to finish by telling you the C2 story. Of course, I have a favorite in this. I like the molecular orbital way of analysis, and it's okay. Richard will give you an example next week of what you can do with atoms and molecules. So I just want to show you what you can do around this simple example. It'll take me 5 minutes more, around C2. So I already have prepared the story. There's the ground state of C2, 12 excited states of C2, the molecular orbital curves. Can we understand this? Sure, we've prepared you for this. Here are the orbitals. There is the orbitals. I will reproduce them here. There is a sigma bond. There is next one lone pair combination. I'll call it LP, which is slightly anti-bonding. And next is a pi level, which is bonding. And next is the sigma, the next lone pair combination, which is slightly bonding. And the ground state of C2 is C2 has 8 valence electrons, N2 had 10, C2 has 8, fills through here. That's the ground state. It has a bond length of 1.24. What do you expect for the excited states of that? No problem. Let's look at them one to one. The lowest excited state takes 1 electron from here and pushes it up to the next one. That takes it from a strongly bonding orbital to a slightly bonding orbital. It's going to lengthen the bond. Look at the bond lengths up there relative to the ground state. The next excited state takes 2 electrons from here and pushes them both up to there. Take a look at the next one. That's the triplet sigma G minus. Now let's jump to the shortest and the longest. How can you get a bond in an excited state shorter than a bond in the ground state? The excited state that's involved is a very interesting one. Takes 1 electron from here and puts it up there. Takes it from a slightly anti-bonding orbital and puts it into a slightly bonding one. It doesn't shorten by much, hundredths of an angstrom, but it shortens. How can you get a long bond? That long bond of 1.53 is formed by occupying the pi star orbital, which really does violence to the bonding. So you can explain, and you know, it's not just me. This explanation on 3 valence levels, which is all he had in 1932, is what made spectroscopists believe Mulligan and Hund. This is an important point in the credibility nexus of molecular orbital theory in one community, which is spectroscopists. And it goes back to the 30s. Though it's been largely forgotten, we can now do it for 12 excited states. I can make sense of these, but it's not only these. Let me show you some other compounds. C2 is in a gas phase. About as far away from C2 in chemistry as I can get are a bunch of molecules containing C2, which are things of the composition like erbium-10, ruthenium-10, C19. God forbid we should show this to first-year students. Please close your eyes. No one's going to ask you to calculate the oxidation state of carbon in that molecule. We shield our youth from such perverse complexity, the beauty of all this world, not only from sex. From such things, so that we can't show these things, but they exist. And all of these, here's an example, dysprosium cobalt C2. Some of you may know calcium carbide. Anyone who was a Boy Scout 40, 50 years ago knows what calcium carbide is, has never gotten the smell of a carbide lamp out of his nose, that smell of wet acetylene, which I can still feel to this day. Calcium carbide reacted with water, you get acetylene, which burns. It's the basis of a lamp. Calcium carbide has C2 units with a bond length in a cubic arrangement with calcium 2+ and C2 2-. There are others. Dysprosium cobalt carbide, for instance, which you see here in blue and red, and a structure at the bottom. Dysprosium is the large white balls. There's a layer of dysprosiums, layers of cobalt C2. The cobalt C2 is an organometallic two-dimensional polymer with acetylides in it, di-sigma bonded and pi bonded. If you look at it, where the blue balls are relative to the red balls. Red is carbon, blue is cobalt in this representation. All of these have C2 units in them. The bond lengths in these C2 units, you can see in this table from Wolfgang Jaichko, range from 1.19 to 1.48 angstroms. I can make sense of every one of these in terms of the partial population. How am I going to do it? I'm going to do it the same way I did it the previous one. I'm going to do it in terms of population of various orbitals with a C2 unit. And let me put the story together. And here is a wheel around C2. Upper left is spectroscopy. Bond lengths 123, 154. Up there is ethane, ethylene, ethine, 1.21 to 1.54 angstroms, the same bond length range. You think that's an accident? For organic chemistry. Pete Wolzanski made that tantalum complex with his typical siloxy units and a C2 in the middle. We talked about Mike Bruce, who made that ruthenium compound that we see over here with a C2 being torn to pieces by 4 rutheniums around it in the middle. A cluster with a C2 and cobalt nickels, the organometallics. C2 on a silver 110 surface. 2 things. One is that we can make sense of all this with the molecular orbitals, with the occupations of the C2. The other thing is, and that's really what almost the thing I want to leave you with, and that is nature's trying to send you a message here, us a message. The guys who work on the thing up there are physical chemists, organic chemists, organometallic chemists, inorganic chemists, surface scientists. What nature's trying to say is, I don't care what you guys call yourself, it's only me. There's a molecule, there's bonding of molecules. We have to find a way to understand this. But to get back to the bonding, and this is the view that I would like to leave you with. It's there in the abstract. I come from a philosophical tradition where I am at peace with complexity, even though I make use of simplicity. And I like definitions that are not reducible. I like definitions that don't say, this is a bond, this is no bond, I shut my mind, and that's it. I like definitions which are slightly fuzzy at the borders, so that they make me think about whether there is a bond or whether there isn't a bond in something, and that's what the thing that I want to leave with you. Push the concept to its limits. You saw how rich this concept is, how many different experiments. This thing which has been with us from the beginning is not solved. You can still see papers in Angewandte Chemie about the rotational barrier in ethane or about the bonding in benzene or any of these things. Some people think that that's not a science, if there's still a debate to this day. Some people think that philosophical questions such as their free will or also are not worth of study because freshmen can talk about them in a course 2,000 years after Plato and Aristotle. I don't think so. I think these are important questions. They're going to remain important questions. And my advice is to learn to live with it and have fun with it and then spare us the hype. Thank you.
Hoffman will be happy to take questions.
Yeah, if people have to leave, I understand, but I'd be glad to answer questions, anything. Under the sun, philosophical, religious, political. Not going to tell you how much money I've given to each campaign, but Who am I going to vote for? Yes, Al. Yeah.
The C2 example, which I think I must have learned from you
Yeah.
years ago, I've used in my quantum course ever since.
Yes.
And we explained just as you're pointing out, rationalize all the different bond lengths, and it does work.
It does work, and you can predict others. Dr. Anderson just made a point that that's a useful example, the C2 example. It also, I can't repeat this thing about stability. Let me, something I forgot to say. In the second row diatomics, that is on aluminum 2, silicon 2, on phosphorus 2, sulfur 2, chlorine 2. The most stable diatomic thermodynamically, P2 with respect to atomization, does not exist in a bottle. And you can tell me what it does. That's not one of the allotropes of phosphorus. It is at liquid helium temperatures in a matrix, but not at room temperature. The only stable diatomic of stable in the sense of being in a bottle, not being very healthy for you, is a green gas called chlorine. And chlorine is less stable thermodynamically with respect to atomization than any other diatomic in the first row. Then aluminum 2, then silicon 2, then phosphorus 2, then sulfur 2, and yet it is what exists. So it's not what it is, it's what it goes to, what the barriers are to what it's going to that matter in chemistry. This is why when you see in the literature predictions of stable molecules, you can see in every issue of JACS and Angewandte Chemie 1 to 3 papers predicting these molecules they are weak predictions of existence possibly in a hydrogen matrix, in a matrix of helium at low temperatures. There is no chance, not that there's no chance, actually some of them, interestingly, will survive, a small minority, but the people who make those predictions, they're making really calculations of whether these things are local minima by calculating the vibrational frequencies, and they never bother to, they don't want to calculate, I'm as guilty of this as others too, they don't calculate the barriers to the obvious things, which is dimerization, fragmentation, reaction with oxygen, nitrogen, even with xenon or noble gases, and with water, which are the components of a typical laboratory atmosphere. Argon, xenon. Yes, back there.
Well, you did open a little bit of a Pandora's box with your reference to religion. You said that
Yes.
nature is trying to show us something. How do you distinguish between nature and God?
So, no, I have written a book about issues of religion and Jewish religious tradition and science. I wrote it together with a religious woman, and I myself am an atheist with 2 unusual features. One is that I have a lot of respect for religion, and second is I have a feeling for ritual. But that's just my personal thing. I think nature, there are some people who would find satisfaction alone, and there is a variety of people who are spiritual, as I think I would identify myself, but who are not religious, and to whom the beauty of the universe may be revealed in nature, but may be also revealed in a Haydn trio, or in a song by Bob Marley and the Wailers equally, and who also find that I find science to be a spiritual as well as a material enterprise. I think the understanding of how DNA works is a spiritual achievement, and gives me as much pleasure. Now, does it do the other things? Like, does it give a foundation for an ethics, for instance? which is what we usually attribute to religion, though God knows it has not prevented people from killing each other, right, for religion. But I think you can work your way through an ethics to an ethics, and I think not from a sociobiological viewpoint either, which I have troubles with. Basically, I'm an instinctive leftist, so that I have troubles with sociobiology, but I also have troubles with the connection of sociobiology to deterministic reductionist viewpoints, which is part of what you see me fighting here. I'm fighting here to establish an intellectual basis for chemistry which is based on that partial knowledge, on some of it tacit, some of it implicit, a basis for chemistry which comes out, I think, much more from the real world than the reductionist analysis. You will hear the reductionist analysis next week. I haven't answered the question. Yes.
If you're saying bonds are this fuzzy idea, what do you think of atoms? This is more of a physics question, but the subatomic constituents.
So I think the atoms are more real than bonds, but the reality of the bonds, just because something is fuzzy doesn't mean it's real, that it's not real. It's enough to kill you. If you breathe in HCN, it's going to kill you, or carbon monoxide. And I know how it does that. I'm fuzzy. I'm maybe fuzzy about how carbon monoxide bonds to hemoglobin. It bends a little. But I'm at the nature of the bonding, but I'm basically a naive realist underneath, as all chemists, I think, are. I just don't want to parlay that naive realism that compounds are real into a certainty about knowing what nature is. I think all our approximations are their approximations, their approaches. And I think it's what some people cannot get through their head is that it's possible to do precise things with imprecise tools. Take the language, any language. Let's take English, our language. It wasn't my original language, it's my language now. It's imprecise. You'll do a chain of lookups in a word, and you see dog is an animal of a certain kind, then you look up animal, you look up, and eventually it'll circle in about 5 or 6 lookups. Languages are inherently imprecise, and yet out of those imprecise tools, people can shape the direction for directing a fire engine to the fire so there's no trouble, and can write beautiful poetry, right? And do science with imprecise language. I think that's wonderful. And I don't think you have to assume from the fact that you can do wonderful, precise things that the underlying tools for doing so have to be supremely well defined.
I'm wondering if you talk it out to these companies that make this chemical software nowadays that allows students now to afford to buy it and give you beautiful pictures of orbitals and bonds.
Yes.
And you ask them to put in cautionary language into these programs, or?
No, it's just like, you can put in all the cautionary language in the world, it's not, you have to learn it yourself. The wonderful place where we learn it, probably less so the classroom than that wonderful social structure of a research group at a university like ours or mine, where in those discussions you allow yourself to say this work is a piece of junk. Can't be true. You can't say that in public. Or you talk about something, you sense the enthusiasm of the professor about something, you sense the uncertainty of the student about this. Is there a bond there or not? And it's in dialogue that a lot of understanding. This is why I think the American educational system is so good at the graduate level. We do everything wrong in grade school and kindergarten, and they're on through the end of high school, and so that we're typically 2 to 3 years behind. In college, we do something different from the rest of the world, and I'm proud of what we do. I think a liberal arts education is just that, or we aspire to it and we approach it in various ways. And I'm very glad to see that a chemistry professor is teaching one of the writing courses here. But the net result is by the end of college, you're still 2 to 3 years behind because you've taken those humanities courses. By the undergraduate schools, the Americans have caught up. We do everything right in graduate school. I know some of you have proficiency exams coming up, don't think so. But we do things right, and part of it is this research group structure and the way we talk about things. It's for the undergraduates, the quicker you can get into research, the better. You will see the real world open up on a personal family level almost that is hard to imagine.
Any other questions? Thank Professor Hoffman again.